Hey, welcome back to Engineers Workshop. I'm kind of on a roll with the Skinner videos, so we're going to move right into the next part of that engine that I wanted to talk about, which is the slide valve and the steam chest. But before I do that, I need to make a correction. Year's only half over, and already I've used up my mistake for the year. So in the previous video, I said that the horsepower calculation for a steam engine was the formula PLAN, which is average pressure times the length of stroke in feet times the area of the cylinder in square inches times N, which is the number of power strokes per minute, divided by 36,000. It's actually PLAN divided by 33,000. Which does nothing but make the engine more powerful because it's got a smaller number on the bottom. So in actuality, that engine is 130 horsepower with 150 psi boiler pressure input and 300 RPM. So I want to move on now and talk about the slide valve and the steam chest. Before I break down this setup, I wanted to point something out. If you recall, the apparent center of the eccentric moved from one point at wide open throttle to another, and the stroke decreased. But this move occurred essentially along a vertical axis, pretty much following the laser line that you see. And if you recall, we have this engine at front dead center, and this moved this way for a reason, because everything that happens on one side of the stroke for the slide valve has to be mirrored on the back side, because both sides of the piston see pressure. It's a double acting engine. So the move has to be symmetrical. The only way to do that, make it symmetrical, is to move vertically. That way, the timing events change the same for both the forward and the backstroke of the cylinder. The other reason is because these engines could run in either direction. Now this engine, as we're looking at it, has a normal direction of rotation that is counterclockwise as viewed from the flywheel. But in order to reverse the rotation of the engine, what you do theoretically is you take the entire governor mechanism off. So you would take the eccentric rod off, then the entire governor could be disassembled, flipped 180 degrees, and rebolted back to the flywheel. And that would shift the lead 180 degrees from where it is, and then the engine would run in the opposite direction. It would run clockwise. That would mean that the pivot point here, which you have room for it in this location, the pivot point for the spring would change. The stops would stay the same, they would just reverse. And what you would have to do is the pivot point for the actual governor would go onto this spoke, and the tension rod would go into this boss here. Now, I'm noticing that this boss is not drilled for the tension rod for the spring. So there's a little bit more work to just, flip-flop in the governor in order to get the engine to run in the opposite direction. You would have to make some modifications to the flywheel. And it looks like they've accommodated it, but because they do have the casting for it, but it's not universally drilled and tapped and set up so that it can run in either direction. So we're stuck with running in this direction. We'll just make all of our line shafts and counter shafts work with that as it is. The other thing I wanted to point out is that every Skinner engine that I have seen online has a different type of eccentric rod actuating the slide valve. The pivot point is the same, and it has the rocking action to reverse it, but it comes back to more like a rod end. It just has a spherical stud out here with a little mating female spherical seat. It does not have this huge, ungainly, this is a journal that is babbited, and it has a split bearing cap that traps against that, and it's actually spherical because this is not a straight line motion. Because that's a pivot, that end is actually pivoting on an arc, so it's doing this, as it rotates back and forth. And you can't just have a straight babbited journal surface. You have to have a spherical so that this rod can pivot in and out as it's moving back and forth. So I have an idea where I think I'd like to re-engineer this. I'm going to make a reversible change to this engine and replace this end of the eccentric rod, and it unbolts here. So I can use everything from that point forward, but use a modern spherical roller bearing, and all I have to do is make an offset holder to hold that spherical roller bearing in the correct place, and I won't change any of the timing events, but it'll just be much more, much smaller. It'll do the same job. It won't have the issues with play and having to, possibly re-babbit this surface. This has a large steel guard to contain the oil splash, and it's fed from the oiler into this cavity, and all of that babbit surface is oiled by that system. So that's for way down the road when I have the machining capabilities to do it. But let's move on to the steam chest and slide valve. Okay, the steam chest cover has, I believe these are 3/4 inch studs and 1 7/16 hex nuts. So this is pressurized, in this case, to 150 psi. And normally on a conventional slide valve engine, the valve is seated against the face of the valve ports by the pressure in the steam chest. And when you pressurize the steam chest, that valve will actually snap tight against the valve ports. This engine has what's called a balanced slide valve. The slide valve actually is hollow, and there's an external piston that is pushed against the backside of the steam chest cover. So the backside of the steam chest cover, instead of being just a rough casting, has a machined surface for that balance piston to ride on. And what the balance piston does is it takes most of the pressure off of the face of the slide valve. I wanted to figure out how much pressure was actually on the slide valve in a conventional engine without a balance piston and one with a balance piston such as this Skinner. And so I started looking at all of the areas of the exhaust ports, the exhaust port being in blue, the intake ports being in red, and then here's all of their dimensions, 8 inches high by this wide, until I realized that really none of this matters. Yes, the exhaust is at 0 pressure, but what really determines the clamping force of the slide valve is the area of the slide valve itself. So when you look at that, the slide valve is 9 3/4 by 8 9/16, and then it has a cutout in the center that's 8.75 by 5. So this area in the center in blue, which is 44 square inches, is at 0 pressure essentially, because it's open to the exhaust at all times. And then the outside of the slide valve has 150 psi surrounding it. So the thing that you have to consider is what happens across this face. Well, basically there's an analog equivalent that if the pressure starts out at 150 psi here and goes to 0 here, it basically forms a triangle and it just bleeds off linearly. So you can look at the area in yellow as if it has the average pressure of 150 plus 0 divided by 2, or 75 psi on it. So we have 83.5 square inches that is at 150 psi. We have 44 square inches we subtract off of that, that's at 0 psi, and we have some back pressure of 40 square inches that applies, pressure counter to the steam chest pressure. So I was really surprised. This is 12,500 pounds on the steam chest from the 150 psi. So you're stacking like 3 SUVs on top of this thing, and that's the pressure that this would be seeing. Well, minus the back pressure, there is 2,900 pounds of back pressure from the pressure that bleeds across the face, but the net pressure is still almost 10,000 pounds, 9,500 pounds.
And then, that's a cast iron piece, and then you're dragging this back and forth on the surface. And if you look at, mu as 0.1, it takes 954 pounds to drag this slide valve back and forth. So what a balance piston does is you look at the area of the balance piston, which is 9 3/8. Then the center of the balance piston is 8 1/4. It kind of has the same effect. It has an effective pressure of the balance piston of 4,500 pounds. Now, this is subtracting from the pressure that's applied to the to the slide valve by subtracting the amount of area that 150 psi acts on. And what you end up with is you take the 9,543 pounds, and that brings it down to 1,524 pounds. Now, you would think that the friction force reduces by this much, but actually now we're dragging both the slide valve back and forth against the surface, and we're dragging the balance piston back and forth against the surface. Those two forces come down to 152 pounds and 117 pounds. The sum of those is 269 pounds. So the forces to move the slide valve back and forth go from 1,524 pounds without a balance piston to 269 pounds with a balance piston. Definitely need one when you have a full pressure steam chest.
So what we're going to do, we're going to take this off, and I'll show you the back side of this steam chest cover, because this is going to go off to Dave Richards, and I'm sure you know him, Old Steam Power Machine Shop. Check him out if you don't. He's agreed to reface this back surface. I have some footage where I took this off and I didn't know what the condition was. I might show you that next, but we're going ahead and pull this off, then I'll give you a good close-up of the surface of this steam chest cover, and also explain how the balance piston works for the slide valve. This lubricator is driven by the bell crank that reverses the direction of motion for the slide valve, and it's just a ratchet. So when the slide valve is moving a very small amount, you're going to get a very small amount of lubricant. And when the slide valve moves a large amount, you're going to get proportionally more lubricant. So we got to take this off, because we're going to take the steam chest cover off. Got to be careful, because once the steam chest cover is off, there's really nothing holding the slide valve in place, and it kind of wants to tip forward.
Now at this point, what I need to do is get a piece of flat bar slid in behind the face of the steam chest cover to act as a stop to prevent the slide valve and balance piston from falling when I remove the steam chest cover. So I'm trying to rig up a bar clamp behind it. And yeah, we won't even talk about that. Just trying to get the steam chest cover to move off of the bolts. And once I get all this rigged up, which only has to last for a few seconds, we'll be able to pull that 100-pound steam chest cover off.
This is the slide valve, and this outer part is the balance piston. And these are the ports: intake port, exhaust port. I thought these were rivets. It appears they're screws. Interesting. Nice brass tag there. Erie, Pennsylvania, number 11186, 11 by 12. So we've got a sealing surface here and then a raised area that represents the approximate travel of the balance piston and unmachined casting there. So the back side of the balance piston, which is this surface, is reciprocating back and forth by the action of the slide valve. And you can see where this thing has definite horizontal scratches in it. It's supposed to be able to float and rotate, but I think once it locks into position, that's the end of its pre-rotation. And you can see the witness lines here, this eyebrow or eye-shaped area. That's the maximum travel of the valve. So it's probably 2.5 inches when you go from here to there. Back side of that balance piston will be going back and forth, and then as the machine governs itself, that travel is going to become less and less. Some kind of a copper repair in here. This area, the unworn area, you can definitely feel has it's raised compared to this. I would say several thousandths, at least maybe 5. But Dave's gonna machine this all down and give me a nice flat surface within 1/1000ths. Then I might send this up to Daryl Griffin in Michigan. He loves to scrape things in, and we can have him scrape this for an oil retention surface. This one I'm just going to have machined locally. I'll have this kiss ground at Henrico Tool and Die. And then we'll have a good seal on this surface. Okay, this is the main face of the slide valve. And you can see here that it's got some issues with horizontal scoring on both of these faces, and it's got some vertical pitting. It's really not very deep, but this needs to be resurfaced. And this can be ground, and it does have a flat back surface to reference from, but I'm going to have this ground locally so that this is perfectly flat. And then we will address the face of the steam chest separately. But what I wanted to do to show the timing of this is I made a cutaway. I think Dave Richards did something similar. I made something that would mimic the slide valve. And the geometry of this block of wood has the exact same length, which I believe was 8 9/16, and then the exact same lap marks to the exhaust area. And where I've cut this out, that's pretend that's going to give us access from the pressure ports on either side of the cylinder to the exhaust port on the steam chest. And then this back face is exactly on a plane with this cavity, which traps the end of the slide valve actuator. So I'm going to put this on the engine and you can see a little bit better what it's going to tell us. Okay, I have the engine set up with the governor relaxed, so we'll call that wide open throttle. It's maximum stroke. The engine is at front dead center. I have two cameras. I'll keep this camera set up on the flywheel to show you where we're moving it.
Well, before this video just gets too long, I'm going to stop myself right there, and we'll pick back up in a part 2 for the slide valve. So I hope you enjoyed this. I'm learning a lot about the valve timing and how things work with this governor system. And give me a few days to keep editing video together, and I'll put together another segment finishing up this series on the Skinner 11x12 steam engine slide valve and governor system. Catch you next time on Engineer's Workshop.